Ahoy again. So we've seen two different versions of Hutton's razor, one typed, one untyped, and the natural question is how these two versions are related. So almost obviously, if you have a typed expression, then it should be possible to get an untyped one just by forgetting the type. So let's see if we can do this. So pattern matching on the E, do the traditional renaming. Okay, I reload the file, and then we see that if we have a number, then we know that it's a number, but it doesn't really matter. We can just also have a number without knowing that it's a number. Similarly for bits. And here we know that E and E prime are numbers. Let's forget about that. And let's add up the results. Right. And the same way here, we can just do an if then else of the result of forgetting the pieces. Like that. Okay, so it's easy to forget information that you have, but the challenge is to go the other way, to go from an untyped expression to a typed expression. So in aid of this, I defined this record constructor of what it means for an untyped expression to be well typed. I'm saying that it means that there exists a type tau, a typed expression t which has type tau, and the proof that if I forget the type of t, then I get the untyped expression. Right. And with this information, I should be able to take an expression e and maybe infer that it's well typed. So this is like type inference for this expression, right? And some cases I will always succeed, some cases I might fail. So for numbers, I know that this is always going to succeed. So say it's a just, it's going to be okay, and the type is going to be not. And the expression is going to be the same one, but now at a different type. And the proof that if I forget the type of this, which I did up here, num_n, I get num_n, well, that's just REFL, right? And it's the same story for bits, and it's so easy that I can even ask Agda to do it. Or rather, it's so constrained that there's only one good answer, so I can ask Agda to do it. Here, on the other hand, it's a little bit trickier, right? Because if I first infer the type of E, and it's not a natural number, then the whole thing should fail. So this is another job for a do block, where I start by inferring the type for E, it's going to be okay, and I'm going to insist that the type here is a natural number, but I'm leaving the T and the P unconstrained, right? But because I haven't covered all the cases here, I'm just complaining that there's incomplete pattern matching. I've only matched the case where this is not. So I have to add in another one of these catch-alls, or if it's anything else, then return nothing, right? Okay, and then I can do the same thing for E prime, just putting in enough primes, like that. And if this both succeeds, then I know that I can return just, okay, end result is still going to be a not. This is going to be t plus t prime, and I need the proof here that t plus t prime equals e plus e prime. But I have the proof for the pieces, so I can do this with a Kong, except now it's a Kong where I have two places to fill in proofs, right? So that's Kong 2 from the standard library. Like this. And then here I need the proof that t equals e, that's my p. And here I need a proof that t prime equals e prime, that's my p prime. Right. Okay, and then here for if then else, it's similar but not quite the same, right? So we start by insisting that if we infer the type of e, it better be a Boolean. Okay, and then this might fail, so we better put in a catch-all. Like that, and then you might think that we should do the same thing for E and E prime. except now we don't really care what the types of these things are anymore, right? So actually these are unreachable. The only way this could fail was if the pattern match got back a specific thing we're not matching. The whole thing can fail, but these clauses are just about what happens if this pattern matching fails, right? So we don't actually need these here. Okay, and then here we would like to return just, okay, tau if e t, then t prime, else t double prime, and then a proof. But we see that this doesn't work because in our typed version we insisted that the types of the two branches were the same. Right, okay, so sorry, I know what I'm supposed to get for an error, but I get a much simpler error first. So if I do that and try to give that, then I really get this error, that the types are not the same. So you might think that you can fix this by just changing them to be the same here, but we see that we still get the same error because all we've done by doing that change is to make this new variable shadow the old variable. Because remember that things here are patterns, so by introducing a new variable of the same name, we're just shadowing the earlier one. We're not insisting that they are the same. We have to do this work ourselves. So what we need is something of this type, where we take in two types, tau and tau prime, and we maybe say that they are equal, right? So if we had that, to put it up here, if I had that, then we can do another pattern match and insist that this proof is refl, right? Tau equals tau prime. Like that. And then in the rest of this block, we know that they are equal. So we can actually return this. And in the same way, an easy way to make these two equal is to just pattern match and all the proof that the pieces are equal. So say that this is refl, and this is refl. Then that changes the type of the rest of it, and we see that the proof of this is refl. So that's an alternative to using a con. But before we're happy, we still have to make this proof, right? And because I'm lazy, I'm actually going to do this in a slightly different way. Instead of proving maybe this, I'm going to prove that this is decidable. And then I'm going to use dec to maybe, which turns decidability proofs into maybe proofs by keeping the yes case and throwing away the no case, right? So if I had this one, then I can do a dec to maybe of that to turn it into the maybe I want. So it's quite convenient for me here to have a maybe, because then I can use it in the do block to pattern match on this thing. But to construct this one, it's really convenient to have a dec, because now if I first pattern match on x and y, then there's only one possible answer for each one of these. So I can be lazy and just let auto figure it out. Whereas if I try to do that directly down here, then auto will just return nothing for me all the time, because nothing is always an option. But this type is so precise that there's only one answer, so it must be the good answer. Okay, so that was the missing piece we needed for that. And we can now define a new evaluator for the untyped expressions if we want, right? Where what we do is we first infer a typed expression for e, and this of course might fail, so that's why we still have a maybe. And But if this is okay, all we really care about is that we have a type expression t, and then we can use the typed evaluator for t in order to get a value. And finally, we can also forget from typed values to values, right, for every t. And this is not hard to do. Right, so the way to do it is actually to pattern match on the t, right? So if, let's just leave this as a whole for now, pattern match on the t. If it's not, then the map from t-val t to val is num. If it's bool, then it's bit, right? Okay, so now here I can return just of forgetting the value of t-val t. And if we look at our original examples, just change this to the prime versions, then we see that we get the same results here, right? Including a nothing for this one, because the infer will fail for it. And if you have enough stamina, you can prove that eval prime and eval really coincides, right? But it's quite messy because of the maybe that gets in the way. So to summarize what we've learned, there's an obvious way to go from more information to less information, just throw it away. But if your expression is well formed, then you can also go the other way, from less information to more information. And using this, we can factor our unsafe evaluation into an unsafe infer plus a safe evaluation. And if you think about it, this should be slightly more efficient, because we're only checking for type errors once when we infer it, and then when we actually evaluate, we never up here. This is quite straightforward, right? Whereas this version has hidden all these checks if it's a nothing or a just all the time. So this is more efficient, and by factoring it out for infer, the resulting thing here should also be more efficient.